Okay, welcome to Let's Get to the Marks. Going through GCSE Chemistry Paper 2 walkthrough for the higher paper for AQA. Takes an hour and 45 minutes. Obviously, the walkthrough won't take that long. I suggest you press pause on the video at the start of the question, grab a scrap piece of paper, have a go at the question, and then watch the answer to the walkthrough. Or you can sit the paper. You'll find these all on the AQA website, and then you can watch the walkthrough to go through. Sometimes the mark schemes that come with a website and you find online don't explain exactly how to do the questions, and that's what the aim of the walkthrough is. Make sure you hit the like, subscribe to the channel, and share with as many people as possible to help out the channel so I can get more of these videos to help you smash your exams. All right, guys, let's get into it. All right, here's question one. Let's have a little look. Get out my annotation. All right, one. This question is about fuels and energy. Figure one shows the percentage of electricity generated in UK between 2007 and 2017 using oil and solar energy. We've got the percentage of electricity generated here on the side. And at the bottom, we've got some dates: 2007, 2009, 2011, 13, 15, and 17. And we've got a key. And the key tells us what the color bars mean. So we've got oil here with these blank white bars, and we've got solar energy here with these black bars. Describe the changes in the percentage of electricity generated in the UK between 2007 and 2017 using both oil and solar energy. And it specifically tells us to use data from figure one in your answer, which means when you make your description, back it up with some numbers, because that's the only way you're going to get all the marks. Now, the fact that this is a describe question, this means you don't need to explain any science. You don't need to talk about solar energy being renewable, about light energy being converted into chemical energy. You don't need to do any scientific explanation. It is purely a look at the graph, describe what you see, and back it up with numbers. So let's have a go. So if we look here, in 2007 to 2009, we can say something straight away about the white bars, the oil. Well, what can we say? Well, it looks like 1.123. It looks like we're at 1.3% in 2007. The electricity generated by oil was 1.3. And then in 2009, it was up to 1.6. So we can talk about an increase there. Is that 1.6? Yeah, I think so. I'll never know with my eyes. 6, 7, 8, 9. Yeah, cool. Now we can also say, however, the amount of oil used decreased after 2009. And then we can back that up with numbers. So you could use any pair of numbers here. So we could say from 2009, it went from 1.6 to what is that over here? That's 0.9 in 2011. We could say, so that is a 0.7% decrease. We can say this was a 0.3% increase. So you see, you can talk about the difference in the percentage increase, or you can quote both numbers. So you can say from 2007 to 2009, it increased from 1.3 to 1.6. And then you can say from 2009 to 2011, the amount of oil being generated, the amount of oil used in electricity generation decreased. And give an example, it went from 1.6 to 0.9. Now let's turn our attention to solar energy, and let's say what we can see here. So in 2013, the solar energy, my eyes are so bad, I'm gonna pick that up. What's that? 0.7? Looks like 0.6, looks like 0.65, 0.7. So, all right, I'm gonna go with 0.7, even though you might be able to get a different read on that. And that went up to 2.5% between 2013 and 2000. Oh, they want 2007 to 2000. Yeah, so anywhere along there. So solar energy increased rapidly from 2013 to 2015. It went up by 1.8%. So we've got an increase there. In fact, it carried on increasing up to 2017. Or we could actually say from 2007, it wasn't even 1%. 2009, not even 1%. But we've got an increase in solar energy between 2007 and 2017. And we can give an example. So it wasn't even 1% here or here. And then if you wanted to go right to the end to 2017, it goes right up to 3.4%. So we've got like a 3.3% increase from 2007 to 2017. But you can quote any pair of numbers. And you can even point out here with the oil generation between 2013 and 15, it looks like they stagnated. They stayed the same, the two white bars. So there's loads of different data you can put up as an answer here that will get you those 3 marks. Loads of different descriptions of patterns going up, going down, staying the same, and giving the numbers to quote. You can either say the difference or you can say the starting number and the final number. All right, let's move on. Okay, 1.2, oil contains carbon and some sulfur. When oil is burned, the products of combustion may be released into the atmosphere. Explain the environmental effects of releasing these products of combustion into the atmosphere. So here we've got the word explain. This means we do need to give some science in this as well. We need to actually explain how these products of the combustion damage the atmosphere and the environment. Okay, it's a 6 marker. So pause the video, grab a scrap bit of paper, have a go. All right, let's go through the answers. Right, first of all, we can break this into 2 sections. Oil contains carbon and sulfur. So when it's burned, what will the carbon form? Think about it. Carbon plus oxygen. What's that going to make? It's going to make CO2. What do you remember about CO2? Well, carbon dioxide, first mark on the board, is a greenhouse gas. Let's just change the old color there because red is not suitable for everybody. So carbon dioxide is a greenhouse gas. What do greenhouse gases do to the environment? Causes global warming. What does that result in? That results in climate change. You could say that the carbon dioxide traps infrared radiation if you want. You can expand on that part of it if you like. I'm just going to go through as quick as I can. So carbon dioxide, greenhouse gas, causes global warming, climate change. What are the results of climate change? So we always remember the ice caps melt. What does that lead to? Leads to flooding. Obviously, I could have said before that sea levels rise, because that would then fit nicely into flooding. And what can flooding do? Well, you can lose habitat loss, loss of biodiversity, etc., change in distribution of organisms. Obviously, if an area becomes flooded, organisms that prefer plants and animals that prefer a flooded area will live there. So it's going to change the spread of organisms on the earth and their positions. But also global warming could lead to droughts. Now, I know that always sounds a bit weird when you're talking about flooding, but some parts of the earth are just going to get warmer and drier, could lead to droughts. Crops fail, and famine. Famine is when there's not enough food to feed people and people starve to death. So pretty grim stuff. So crops fail, famine, forest fires, again, loss of habitats, etc. Now that is all I've just been banging on about carbon dioxide, and you can pick up at least 4 marks here for any of these 4 points. Will grab you 4 marks. Now let's write about the sulfur. And what do you think happens when sulfur burns in oxygen? You get SO2, and that is sulfur dioxide. And hopefully you can remember what are the issues with sulfur dioxide. I'm going to do this one in a different color. So sulfur dioxide forms acid rain. Basically, it reacts with water in clouds, forms acid rain, changes pH of soil and water, and that will kill fish or any marine organisms, doesn't just have to be fish, and trees. So that's going to further increase, destroying the trees is deforestation. It's going to contribute to global warming as well, very indirectly. But sulfur dioxide, of course, acid rain changes the pH of the soil and the water. It could kill fish, kill trees, damage buildings, um, things made of limestone, damage cliffs, damage rocks. Anyway, I've kind of got 4 marks there. I don't need as many marks here, but this would get you at least 3 marks here. So you can kind of have 4 from one, 2 from the other. You're going to need to say at least a couple about each of these, but that's going to get you all the marks. Let's move on. Suggest one reason why solar energy is more sustainable way of generating electricity than burning oil. So, yeah, why is solar power a more sustainable way of generating electricity for your home than burning oil? What do we know about solar power? It is renewable. What does that mean? I probably should say it is a renewable resource. Okay. Oil is a fossil fuel and renewable. So it's going to run out. Oil's going to run out in our lifetime. The sun will not run out in the lifetime of the human species. We've still got billions of years left. We're likely to be extinct by the time the sun runs out of energy. So, for all intents and purposes, solar power is renewable. 1.4, solar energy may not be able to replace the generation of electricity from fossil fuels completely. Suggests two reasons why. Why can't we rely on solar power all day and all night? Obvious reasons. Um, it is, yeah, yeah. Well, like cloudy days, not as much. I'm just giving examples. Solar power, um, at night, not as much solar power. So you can't generate as much electricity at night or on cloudy days. You can't be guaranteed. Um, not all places on the earth receive sufficient sunlight for solar power. Like there's places on the earth which actually don't get more than like 8 hours of sunlight a day. So they're not going to get enough solar power to run train stations, to run hospitals. Hospitals have to be kept on all day and night. That doesn't mean solar power can't be stored in things called capacitors, but it's very unlikely that we will ever achieve total electricity generation by solar power unless we take something up into outer space by the sun so it's not interfered with by clouds and the earth the rotation of the earth. So if we have some sort of storage facility up there, but that seems highly unlikely. Okay, how did you do? Let's move on to the next question. Past papers are an excellent way to revise for exams, so make sure you keep at it with these old past papers. What I need to do here is just duplicate this because they're going to ask us to plot a graph here. So bear with me, peoples, as I sort this out. All right, guys, here we go. Hopefully you can see this. Right, what we're going to do here, we are looking at this question is about alkanes. It shows information about some alkanes. Number of carbon atoms in an alkane molecule in the first column of this table, 4, 5, 6, 7, 8, 9. Boiling point of alkane in degrees Celsius, 0, 36, 69, missing number. And for 8 carbons, it's 126, 9 is 151. Plot the data from table 1 on figure 2 over here on the graph. So let's go ahead and do that. Of course, the difficult thing with the graph sometimes is working out how much each little square is. So how do you do that? Well, look at the vertical, the y-axis over here. There is an increase in a number from 20. So we've got 20 for 5 little squares. So what you do is you go 20 divided by 5. That tells us that each little square is worth 4. So each square on the y-axis is worth 4. Now, in a triple science paper like this, it probably won't be the same on the x-axis. So you need to work your scale out for the x-axis. So here you can see we've got 1, 2, 3, 4, 5 squares in 1. So we basically want to do 1 divided by 5 equals 0.2. So each square is worth 0.2 on the bottom. Okay, it doesn't really matter because we've got whole numbers here, so there was no need for me to do that, but you might be in a situation where you need to work that out. All right, let's zing these on. So when there are 4 carbons over here, start at 4, the boiling point of the alkane is 0, so we're going to go bish there. When there is 5, it's 36, so we're going to go 20, and we said these are 4, 24, 28, 32, 36 is 1 below 40, 1 square below 40. Then we're going to go 6 over here and to 69. So we're going to come up to 60. Each one's worth 4, so we're going to go 64, 68, and then halfway on that square. Remember, in the exam board, they say you're allowed to be one of these little squares out or half a little square out. So don't worry too much about that. 7, we can't plot that on because we don't know it. 8 is 126. So we're going to come to 120 and then 124 and then halfway again in between two little squares. So there we go. And then 9 is 151. So we zing up here to 140, 148. And that would be 152. So again, another half square. And there we go. That is all of our points. And that's going to get us 2 marks. Whoa, that's going to score us 2 marks. Of course, sometimes in a graph, they want you to label the axes as well. So there's another mark. They want you to draw a line of best fit. Well, let's see what they want us to do here. So let's zing down. Predict the boiling point of, so what we need to do is predict the boiling point of X with 7 carbon atoms in a molecule. Use table 1 and figure 2. All we need to do here, guys, is follow this up and put it so it would fit in line. So I would go about there. I reckon its boiling point is about 100. Now, is the exam board, so that's the one for X over there at 7 carbons, is the exam board going to mind if you put it like, if you put it in a slightly different place? No, they're going to give you a bit of a range, I would suggest, between like 102 to 100 to like 90 something 5 or something. Because as long as it's in a certain range and fits that pattern, you're all good to go. So I'm going to go with 100. And there we go. Right, let's move on. Get rid of that 100 there and move down. Okay, do I still need this graph? Okay, figure 2 is not suitable to show the boiling point of the alkane with 3 carbon atoms in a molecule. Suggest why. What is it about my graph? Look, we've got a 4 carbon atom there at 0. Why couldn't we show, why is the graph not suitable for showing the boiling point of a carbon atom with 3? Where would my dot be? It'd be down here. It wouldn't be on the graph. What doesn't my graph have? Some graphs continue down there and they have the negative numbers. So this is the reason why. It would be below 0 degrees and the graph starts at 0 degrees. We would need a graph showing boiling points below 0. So it's not suitable because it doesn't have boiling points below 0. I've longed that answer out. You don't need to write all of that, but you get the idea there. So the last part to this, or the next part to this question, 1.4, state why, what is the state at 20 degrees of the alkane with 4 carbons in a molecule? So saying to you, this atom, this molecule with 4 carbons, this is the boiling point. If it was at 20 degrees, what state would it be in? Well, that's boiling point. So it boils at 0. So what state will it be in at 20? It's going to be a gas because it's above its boiling point. There we go. Awesome. Okay, let's move on. And okay, we've got a repeat of table 1. The alkane with 9 carbon atoms in a molecule is called nonane. Here, this one with 9 and 151. Complete the formula of nonane. So in order to complete the formula of nonane, you need to know the general formula for alkanes. So hopefully you know this off by heart. You should revise it, use revision cards. The general formula for alkanes, hopefully you guys all know it, CnH2n plus 2. So we're going to use that. So what does that mean? That means that here n is 9. So H must be 2 times 9 plus 2. And that is going to give us 20. Okay. Lovely jubbly. Moving on. 2.6, nonane will condense lower in a fractionating column during fractional distillation than other alkanes in table 1. Explain why you should refer to the temperature gradient in the fractionating column. So nonane will condense lower in the fractionating column during fractional distillation than other alkanes in than the other alkanes in table 1. So the fractionating column is hot at the bottom and cool at the top. So I hope you remember with fractional distillation, it's about 350 to 500 degrees at the bottom. We vaporize the crude oil as it enters the tower. Bing, bing, 1 mark. And then they're all vaporized and they start rising up the tower. But as it cools, there is a temperature gradient, hot at the bottom, cold at the top. As it cools, the different fractions or hydrocarbon mixtures condense depending on their boiling points. So the fact that there are small hydrocarbons with very low boiling points, they won't condense until the top of the tower. So smaller fractions with less carbon atoms will have lower boiling points and so condense higher up the column. And there we go. Bing, bing. Oh my good gosh. This question is about paper chromatography. A food coloring contains a dye. 3.1. Plan an investigation to determine the RF value for the dye in this food coloring. So we got the RF value is the distance moved by a substance divided by the distance moved by the solvent. Your plan should include the use of a beaker, a solvent, a chromatography paper. So this is nice and easy. Essentially, what we're going to do over here, guys, we want to, I need to put this all in writing at the same time, but we want to take a beaker. And then what do we want to do? We want to put some solvent in the beaker. Ta-da! And we need to explain all of this. So you can use different solvents. Water's a solvent, but you can use other solvents. Doesn't have to be water. I don't think that's showing up very well. Let's get rid of that. Okay. You're then going to get a piece of chromatography paper. We're going to place that in the solvent. We're going to draw with a pencil line the start line. This is known as start line. Sometimes called the baseline and always drawn in pencil. We're then going to take our dye and we're going to add that to the start line. And we hope the start line goes through the middle of the dot of the dye. Now, another important thing, the solvent must be below the start line. Look, my start line is above the solvent. If the line is below the solvent line, what will happen is the dye will just dissolve into the liquid and into the solvent and it won't move up the paper. What we have is capillary action where the solvent is sucked up the tiny pores, the holes in the chromatography or filter paper. And as it comes up, it brings the dye, draws it up the paper. And that's how we can do all of this business. Now, what also we need to do is put a nice lid on top. Why do we need a lid? This prevents evaporation of the solvent. Sometimes we're using organic solvents like ketones, like propanone, or alcohol like ethanol, and those evaporate. They have lower boiling points than water, so evaporate more easy. We don't want our solvent to disappear, so we need a lid to make sure the solvent doesn't evaporate. Now what we're going to do, the ink will climb up the paper and the dot will move up the paper. Now, also, the solvent will move up the paper. Now, what before the solvent gets to the end, so before it reaches the end, we take it out and we draw a line where the solvent has reached, and we call this the solvent front. That's the solvent front. And then essentially what happens is we're going to take a ruler. That is the best drawing you've ever seen of a ruler. Be amazed. Take that ruler and we're going to measure the distance the dye has moved. And that is going to go on the top of our RF value calculation. And then we're going to measure the distance the solvent has moved. And that's going to go at the bottom. Notice the dye will never move further than the solvent. It can't be have a greater affinity in the solvent than the solvent has in itself. So it cannot move further than the solvent. It will always move slightly less than the solvent. So you're always going to get a decimal, a 0 point number like 0.1, 0.65, 0.70. You're going to get a decimal. So you'll know you've done your RF value wrong if you get a number greater than 1, because that would suggest the dye has moved further than the thing that's carrying it, which can't happen. So that's basically it. And here's the typical answer you should have constructed over here. And that'll get you 6 marks. Okay, let's zing, zing, zing on. Two students investigated a dye in a food coloring using paper chromatography. Each student did the investigation differently. The RF values determined for the same dye were different. So they used the exact same color dye, but the dye moved different distances up the paper. How did the students' investigations differ? Was it that they used different length of paper, a different time, a different size of beaker, or a different solvent? Well, it's actually a different solvent. For instance, some things dissolve well in ethanol. You know, if you've had oil on your hands, you've tried to wash it off with water, it won't come off, but washing up liquid will get rid of oil. So different solvents will dissolve different things better. Yeah, fair enough. Different solvents. Lovely jubbly. Just because you've used different lengths of paper, the distance that the dye moves will still be the same. Just because you've used a longer bit of paper, it still moves the same distance. All right, enough of my whiffle. Whiffle, waffle. Let's go. Paper chromatography involves a stationary phase. What is the stationary phase in paper chromatography? So is it the beak of the dye, the paper, or the solvent? Which bit of the chromatography experiment is not moving? And the answer is the paper. Okay, we call the solvent the mobile phase and the paper the stationary phase. You need to know that off by heart. So revision cards, people. Ba, ba, ba. Question 4. This question is about polyethylene and polyesters. Polyethylene is produced from ethene. Figure 3 shows part of the display structural formula equation for this reaction. Complete figure 3. So you can see here we have the monomer. This is called ethene. It has a double bond. It's an alkene. It's unsaturated. And they make great monomers for making plastics and polymers. Over here we have the repeat unit for the polymer. And there are 3 things we need to add here. So we need to add the bonds, reattach the hydrogen. Now what they've done for us is put the lines outside the brackets. If you're drawing a repeat unit, always put lines outside the brackets. And of course, that's supposed to be a single line, by the way, put a line in the middle. The double bond disappears, you draw lines out the brackets, and then I need to draw this N, but you draw it on the opposite side. And that is the repeat unit of polyethylene. Lovely jubbly, 2 marks. Bosh bish. Oops. Okay, 4.2. Polyethylene is a thermosoftening polymer. Suggest why polyethylene is easy to recycle than thermosetting polymers. So, it is easier to melt as it has a lower melting point. Now, why does it have a lower melting point? This will get you both marks. Lower melting point, so easier to melt. Why does it have a lower melting point? It has less cross links between the layers. So it's got weaker intermolecular forces, essentially. There's intermolecular forces that hold the different layers of polymer chains together. And in thermosetting polymers, those cross links, which are not quite bonds, they're weaker than bonds, they're weak intermolecular forces. Thermosetting ones have more of those, so it's harder to separate them than thermosoftening. Think of a crisp packet or a plastic bag you put your shopping in. That's going to be like thermosoftening, have weaker links. Benefit is it's more flexible. But think about your laptop or your iPad or your mobile phone. The plastic in the case around that is harder, and that is going to be more of a thermosetting plastic with a higher melting point, but also disadvantage, more brittle, more likely to crack. All right. Let's go to this question here, 4.3. Ethene produces different forms of polyethylene. How can different forms of polyethylene be produced from ethene? Um, by using different reaction conditions. So what do we mean by reaction conditions? Um, Maybe a different catalyst or using different temperatures or pressures. So reaction conditions are normally a pressure, a temperature, or a specific catalyst that is needed for specific reactions. Okay. How many times do I say okay? Okay. Oh, said it again. Cheese. Shoot me now. 4.4. Two different forms of polyethylene are high density polyethylene, HDPE, or low density polyethylene, LDPE. Figure 4 represents part of the structure of HDPE and LDPE. So we got part of the units of HDPE and LDPE. Explain why HDPE has a higher density than LDPE. So if you look at this, why would you say this is more dense than this? Basically, if you had the same volume, the HDPE would be a lot heavier than the LDPE. Why is that? And hopefully you've spotted HDPE, the layers are closer together, or the polymer chains are closer together. Therefore, of course, they've got a lot of crosslinks. Here we've got branching. Can you see these branches coming off? These are straight chains. These have branches, and this has prevented the LDPE from getting very close to each other. And so there are less intermolecular forces, and therefore it has a lower density. So kind of things what I want to say here, which are guaranteed to get you the mark. HDPE polymer chains are closer together, so more atoms in the same volume than in LDPE. So that basically is 2 marks there. We're saying they're closer together, which means you've got a greater mass. Remember, density is mass over volume. So I could say more atoms in the same volume or a greater mass in the same volume because density is mass over volume. If you want to know why that is, it's because these have stronger crosslinks and this has got branches, which doesn't allow the changes, doesn't allow the polymer chains to get as close. Anywho, let's move on. Right, figure 5 shows 3 monomers, A, B, and C. Monomer A can react with monomer B and with monomer C to produce polyesters. So we've got monomer A can react with monomer B and monomer C to form polyesters. Draw a circle, figure 5, around an alcohol functional group. So where is an alcohol functional group? Well, we got one here. We got one here. Obviously, it just says draw it around one, but I'm going to show you all the alcohol functional groups. Now, technically, these two at the top are alcohol functional groups. These are actually part of a carboxylic acid functional group. So we probably want to avoid doing that, even though the OH group is still an alcohol group, but here it's part of a greater group called the carboxylic acid group. So we just circle either one of these. Beautiful. Right, what is the next thing? Complete table 2 to show the formula of a small molecule produced when monomer A reacts with monomer B. Monomer A reacts with monomer C. So what is the small molecule that's produced? Let's have a little butchers. Monomer A reacts with C and A with B. Let's have a little looky look. Okay. So check out when A and B react. They're going to do something. This is called condensation polymers. What do you think of when you think of the word condensation? You think of water. And the reason is when monomer A reacts with monomer B, this OH is going to snap off and join with this H, and that is going to form a tiny molecule of water that will be released. And then this bond here is going to join with this bond to the O there, and we get what's called an ester link, an ester bond. But however, look at monomer C. This is a little bit difficult because it's not on your syllabus or your specification, but they're getting you to apply your knowledge to work this out. So again, we might be tempted to go, oh, the OH is going to break off. Well, the H is going to break off on this side, but instead of there being an OH, look, there's no OH here. This is called an acyl chloride. It's actually a bit of A level. This chlorine atom is going to join with that hydrogen, and we're going to get HCl, a small molecule of hydrogen chloride coming off, and this is going to join there. And so you're going to have polymers formed. Okay. So the answer here, we got water, and then we got hydrogen chloride. How did you do? Check it out. That was quite a hard question, a bit of an applied question. Yeah, let's go. Question 5. We're halfway, peeps. This question is about fertilizers. Some fertilizers are described as NPK fertilizers because they contain 3 elements needed for healthy plant growth. Which 2 compounds each contain 2 of these elements? So NPK, first of all, you want to be asking yourself, what does NPK stand for? In the periodic table, you can find out. N is nitrogen. P, because I don't have room, I'm writing it down here, is phosphorus. And K, yeah, you know, it's an alkali metal, it's potassium. Okay. So all you want to do is write out the formula here, ammonium nitrate. Now, you do actually have to know this formula. Ammonium nitrate is NH4 plus, but nitrate, it joins with NO3 minus. So we have the overall formula, NH4, NO3. So does it contain 2 of those elements? No, it only contains nitrogen. Ammonium phosphate. So once again, it's going to be NH4. It has nitrogen, but the phosphate means we're rocking. So actually, yes, that has a phosphate atom and a nitrogen atom in it. Calcium chloride. No. Calcium phosphate. No. Is phosphate PO3 or PO4 3 minus? Okay, yeah, whatever. Whatever, Tom. That's not the right formula there. Yeah, that calcium phosphate is a different formula. Can't bother to work it out right now. Potassium chloride, KCl. It's only got potassium. And then potassium nitrate is going to be K plus, and NO3 minus. So KNO3. It's got potassium and nitrogen. So bing. That's correct. Good. Right. Let's move on. Oh, jeez. My back's hurting. 5.2. Rocks containing calcium phosphate are treated with acid to produce soluble salts that can be used as fertilizers. Name the soluble salts produced when calcium phosphate reacts with nitric acid and phosphoric acid. So when it reacts with nitric acid, we're going to get, name the soluble salts. All nitrates are soluble, so we can get calcium nitrate. And when calcium phosphate reacts with phosphoric acid, you get calcium calcium triple superphosphate. Yes. 5.3. Ammonium sulfate is a compound. Oh, don't you hate fertilizers? Ammonium sulfate is a compound in fertilizers. Ammonium sulfate can be made using an industrial process or in the laboratory. I shouldn't say we hate fertilizers. They've increased the global food production by 50 or 60 or 70%. So in the industrial process, the following steps are used. React streams of ammonia solution and sulfuric acid together. Evaporate the water by passing the solution down a warm column. Collect dry crystals continuously at the bottom of the column. In the lab, the following steps are used. So that's the industrial. So industry and lab are 2 different processes. Industry is what big factories do. They can afford to do stuff which is a bit more dangerous. In the lab, the following steps are used. React ammonia solution and sulfuric acid in a conical flask. Evaporate the water from the solution until the crystals start to form. Leave to cool and crystallize further. Separate the crystals using filtration. Dry the crystals between paper. Evaluate the 2 methods for producing a large mass of ammonium sulfate. One in the lab is going to take longer. It's because you've got to leave it to cool. It's a continuous process, so you never have to switch it off. You just keep adding reactants and it's constantly giving you product. So you're going to produce stuff faster. Here, this is a batch process. You make one batch, you have to wash all your equipment, chuck any leftovers away, clean up, and then make another batch. So this process is slower. However, any mistakes in the batch process, you only lose one batch. If you get a mistake going on in the industrial process, you might lose lots more. So that would be the old evaluation of this process. This question is about cycloalkenes. Cycloalkenes are ring-shaped hydrocarbon molecules containing a double carbon-carbon bond. Cycloalkenes react in a similar way to alkenes. Describe a test for the double carbon-carbon bond in cycloalkene molecules. Give the result of the test. So, cycloalkenes, yeah, pretty cool, right? So here is cyclohexene, right? It's got a double bond there. Of course, what chemical do we use? We use bromine, and bromine is red-brown, but we don't use bromine because it's quite dangerous. We use bromine water, a slightly diluted version, which is orange. And once it joins across like this, you get two bromine atoms attached and the double bond disappears and it goes from orange to colorless. Bromine, water, result goes from orange to colorless. Bang, 2 marks. Hokey cokily then. Let's move on. 6.2. Table 3 shows the name and formula of 3 cycloalkanes. We got cyclobutene, cyclopentene, and cyclohexene, which I just did. Determine the general formula for cycloalkenes. Oh, it's a little bit difficult. Now, we do know that normal alkenes, this is where you might get confused, normal alkenes have the formula, which is CnH2n. So normally, if you have like butene on its own would be C4H8. But look here, you're only, you're timesing by 2, and then we're timesing by 2, and then what's happening? It's dropping back by 2. So 4 times 2 is 8, but we drop back to 6. 5 times 2 is 10, but we drop back to 8. 6 times 2 is 12, but we drop back to 10. So what could we change about the normal alkene formula to take account of the fact that it doesn't double, it goes 2 less than double? So what I would do is say CnH2n minus 2. And so that's going to be your general formula. CnH2n. There's probably other ways you can write this and still get the mark. You'd have to check the mark scheme, but that's definitely one of them. Figure 6 shows the displayed structural formula of cyclohexene, C6H10. So cyclohexene, lovely jubbly. Chlorine reacts with cyclohexene to produce the compound formula C6H10Cl2. Complete figure 7 to show the displayed structural formula of C6H10Cl2. Where do you think, when you get chlorine, where do you think the chlorine is going to join on here? Well, that's the only region that has some space where it can possibly join on. Let's go down and have a go at completing this molecule. So first of all, we need to get rid of the double bond. So we're going to get rid of the double bond, and it tells you we need 10 H's. So let's get those 10 H's out. Let's attach the chlorine. And we're going to find that we're short on H's. So look, we've got 10 H's there. We've got 1, 2, 3, 4, 5, 6, 7, 8. Where do you think the other 2 H's go? Well, look at carbon. Carbon normally, if there's no double bond, has 4 bonds because it's in group 4, and a carbon atom has 4 electrons in its outer shell. So when we look here, carbon should have 4 bonds, and these 2 only have 1 bond where I've attached the chlorine. So what I need to do is attach hydrogen there too. Don't worry about the fact that I put it like that, but there we go. That is lovely jubbly. Calculate the percentage of mass of chlorine in a molecule of C6H10Cl2, and here are the blah, blah, blah. So they want to know how much chlorine is in the whole thing. So hopefully you all know how to do that. You want to do chlorine divided by C6H10, and this is the bit people get confused by, and the chlorine of the total. How much chlorine of the total? And we need it as a percentage, so we need to times 100. Now, all you need to do here is swap the numbers. So we've got Cl2, that's 35.5 times 2. So that's going to be 71. So we're going to put that like that. Then we've got C6. C6 is 6 times 12, so 60, 72. We're going to add this all together. You can do this all in your calculator. H is 1, so we've got 10 of them. So 72 plus 10, that's 82. And then remember, we've got 2 more Cl's, that's 71. So 71 and 72 is 143 plus 10, 153. So essentially we want to do 71 over 153 and we want to times 100. Let's pop that in the calculator and work out what the percentage of chlorine is in this molecule. So 71 divided by 1.53 equals that times 100 is looking like 46.4%. Does it say to any amount of significant figures? No. So you probably get the mark for 46%, or you can say 46.4%, and that'll get you 3 marks. So well done. Get marks for working out the MR and marks for converting into the percentage. Super. Let's move on to question 7. Potash. Potash alum is a chemical compound. The formula of potash alum is KAlSO4 2. Give a test to identify the group 1 metal ion in potash alum. You should include the result of your test. So first of all, can you spot an element from group 1? You get a periodic table in the exam. Don't be lazy. Open the periodic table and check. But hopefully you know potassium, probably off by heart, is an alkaline metal. So what is the test for the potassium ion that's found in group 1? What test can we do to prove we have potassium? Well, we can do something called the flame test. Hopefully you know this from chemical analysis. Pass through the non-luminous, all right, I'm going over the top, you can probably just say flame test, non-luminous part of a Bunsen burner flame. And for those of you that don't know what the non-luminous part is, it's the light blue part of the flame when your Bunsen burner's on the roaring or the really hot flame. Basically, when it's on the blue flame, it's the light blue cone above the dark blue central cone. Right, the result is the ideal answer they like is turns lilac. Okay, you get a lilac flame. However, they should accept pink or purple as well, because it's really down to people's eyesight as to yeah, what they see. Obviously the flame turns lilac, and so that's what I mean by that. Let's zing on. Right, we're on 7.2. Name one instrumental method that could identify the group 1 metal ion and show the concentration of the ion. Problem with the flame test doesn't tell you how much potassium is actually there. Whether it's just a little potassium or a lot of potassium, it's just going to give you a nice purpley, pinky, lilac flame. However, there is one way, and it is called flame emission spectroscopy. Flame emission spectroscopy. And what will happen with flame emission spectroscopy, you will get a certain pattern, and the intensity of the color that we receive that is emitted in flame emission spectroscopy will be darker depending on the concentration. So not only does it identify ions, but it has the benefit of telling you how much is there as well. So it's definitely a better method of analysis. More accurate method of analysis. A student identifies the other metal ion in potash alum. The student tests a solution of potash alum by adding sodium hydroxide solution until a change is seen. Give the result of the test. So there is in potash alum, aluminium, and hopefully you could look and see that aluminium was present. Now, what is the result of the test if you take sodium hydroxide and react it with aluminium 3+ ions? Well, you're going to get aluminium hydroxide, and this is a white precipitate. So it's a solid, goes from aqueous to solid. So the result of the test is a white precipitate. Lovely, bubbly. Now that will actually, that you can make that dissolve, but they're not asking about that here. 7.4, the test gives the same result for several metal. They are asking that here. So the test gives the same result for several metal ions. What additional step is needed so that the other metal ion in potash alum can be identified? Give the result of this additional step. So the problem we have here, and you probably might be wondering what the hell's going on, is that if you react sodium hydroxide with magnesium, it's also white. If you react it with calcium, it's also white. So how do we know that this potash alum contains aluminium and not magnesium or calcium? Obviously, we can tell from the name. Potash alum would be a stupid name if it had magnesium or calcium in, but they all form white precipitates with sodium hydroxide. Well, what we can do here is so basically we can add excess sodium hydroxide solution. Oh my gosh, I swear I have massive issues. Right, add excess sodium hydroxide solution. The precipitate dissolves, so goes colorless with aluminium hydroxide. So, or with aluminium ions. Okay, which shows the presence of aluminium ions. So I didn't even need to say that. I could just say add excess sodium hydroxide, dissolves, or precipitate disappears, or it goes colorless, basically. Super. It won't do that with the calcium hydroxide or the magnesium hydroxide. Right, describe a test to identify the presence of sulfate ions in a solution of potash alum. Give the result of the test. So if you want to know if you have sulfate ions there, got to carry out a test. So first of all, we're going to add hydrochloric, oh my gosh, hydrochloric acid to remove carbonate impurities. Now, it's very important here when you say add an acid that you don't say add sulfuric acid, because sulfuric acid would contain sulfate ions and so would give you a false positive result. Basically, it would tell you that sulfate ions are present, but you'd added them with the acid that you were using to clean. So first add hydrochloric acid to remove carbonate impurities. So you're going to add that to the sample that you're testing. Then add barium chloride solution. So then you're going to add some barium chloride solution. It's going to give us another mark. And the formula for that is BaCl2AQ. Now, the result is a white precipitate forms of barium sulfate. And of course, barium sulfate, BaSO4, is insoluble, hence why it forms a precipitate. So barium sulfate is insoluble and you get a white precipitate. And so there we go. Lovely, bubbly. We're nearly there, folks, he says. Oh, my days. Question 8 is about copper and the alloys of copper. Solders are alloys used to join metals together. Some solders contain copper. Table 4 shows the information about 3 solders, A, B, and C. Solder A, solder B, solder C, melting point 183, 228, 217. Metals in the solder: tin, copper, lead, tin, copper, silver, tin, copper, silver. Solder B and solder C are now used more frequently than solder A for health reasons. Suggest one reason why. So B and C are used rather than A? What do you know about lead? You might not know, but lead is actually toxic. Lead is toxic or poisonous. It is hazardous to human health. Now, if you're wondering to yourself just out of curiosity, how would you know which metals are bad for human health and which ones are okay for human health? Just think about what you eat in your diet. What metals do humans eat? What metal ions do we take in? You know, you get calcium in milk. So calcium, good for us. You know, we talk about iron in your blood. So iron, good for us. We talk about all these different metals. Magnesium people need, potassium in bananas, sodium in salt. So these metals are actually not that bad for humans because our body knows how, has evolved over millions of years to process these metals, use them, turn them into useful substances within the body. Lead is not one of those metals. It's something that is not found naturally in the human body, and our body doesn't know how to process it, doesn't know what to turn it into, doesn't know how to get rid of it and excrete it out of our body. So even touching lead, if it gets into your bloodstream and into your body doesn't know how to get rid of it. So that's why it's toxic, because it's something our body doesn't use. Anywho, if I keep waffling on, we'll never get through the paper. 8.2 suggests one reason why solders B and C have different melting points. So why do you think they have different melting points? So we've got tin, copper and silver, tin, copper and silver. So what could be different about these two, B and C? So they've got different amounts of each element. Um, they have different amounts of each element. They don't have this, although they're made from the same element, they're not in the same amounts. Um, the layers are arranged differently. So I could say that as well. So different melting points, different amounts of each element with different melting points, or the layers or the structure is different. Okay, right. Copper can be obtained by processing copper ores, recycling scrap copper. Suggest three reasons why recycling scrap copper is a more sustainable way of obtaining copper than processing copper ores. All right, so if you've got an old copper cooking pot, why is it better to send that for recycling so it can be melted down and reshaped into, say, a copper vase, a copper plant pot, or something else? Why is that better than going and getting more copper from the earth? Aha. So it does not have to be quarried or mined. So less transport costs and fuels burnt. So when you're processing it, you're probably going to need trucks to go to the mine, dig it out the earth, etc. We could say habitats destroyed during mining. I've kind of already mentioned mining. I probably should get off of the whole mining. And anyway, that doesn't say habitats. That says habitats, whatever that is. Habitats destroyed during mining. What other points can we come up with? So, no electrolysis needed, which uses electricity, because you can sometimes you extract copper using electrolysis, which uses electricity. Um, Less greenhouse gases released, and also copper is a non-renewable resource. So copper's a non-renewable resource, so more copper left in the ground for future generations. So if our generation uses all the copper and we don't leave our grandchildren any copper, then they're going to have real issues with using electricity and the other wonderful things that copper can give us. So it's a really good idea that our generation doesn't waste all the copper and not leave those for our children and our children's 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 children. You get the idea. Lovely jubbly. There's loads more points. You can check the mark scheme in the description. To check out some of the other points. Copper is extracted from low-grade ores by phytomining. Describe how copper is extracted from low-grade ores by phytomining. Right, so phytomining, plants are grown and absorb minerals from the soil that contains copper. So that is two lovely marks. Phyto means light, so, or phyto means plant, sorry. So mining using plants. So plants absorb those minerals from the soil that contain copper. Okay, you probably get a mark for the word plants. What do we want to do? The plants are then burnt. I know, pretty mean on the plants, eh? The ash is mixed to form a solution. Now, there's two ways we can now get the metal out of the ash. So you're going to get a mark for saying the plants are burnt or they're turned into ash, however, bloody, bloody, blah. And the copper is now in that ash. How are we going to extract the copper? Whoops. We can either use electrolysis, which uses electricity, a little bit less environmentally friendly. We can either use electrolysis to extract the copper from the ash solution, or instead, and more environmentally friendly, we can use scrap iron, which is more reactive than copper. So if you've got an old bit of iron that you're going to throw away, an iron saucepan, an iron bike, something made of metal, that you can just use that scrap old iron. Instead of throwing it away, we can chuck it into the copper solution. And as iron is more reactive, it will displace the copper. So we can use scrap iron, which is more reactive than copper, to displace the copper from the solution. And I would say that is a more green affair, but probably less able to be done unless you can gather together lots of scrap iron on a large scale. You'll probably just use electrolysis. So lovely jubblies, loads of marks there to get all four. Right, phytomining has not been widely used to extract copper. Suggest two reasons why. This is a suggest, one of the dreaded suggest questions. What might people have against using phytomining to extract copper? One of the suggestions might be it does not produce enough copper to meet the demand. So how much copper can a plant really absorb from the soil? And on a grand scale, maybe you'd have to burn an entire forest down to get enough copper just to make one city's pots and pans and electrical wiring. So maybe it just doesn't produce the same amount of copper as going down into the ground and digging it up out the ground and mining. It is a new technology, so not all the countries or all the different companies are using it at the moment because it's a fairly new process. Not enough land space. Like I said, you'd need to burn down a whole forest to produce enough copper just for one city. So not enough land space to grow the plants needed. So there's just some of the reasons. And maybe another one. It takes a long time compared to mining. If you think you've got to wait for the plant to grow, which might take weeks and weeks just to get your copper. So there we go. Okay, question 9. A student investigated how changing the concentration affects the rate of reaction between zinc powder and sulfuric acid. The equation for the reaction is ZNS, solid state symbol, plus sulfuric acid, H2SO4, aqueous state symbol, goes to zinc sulfate, aqueous, plus hydrogen gas. This is the method used. Pour 50 centimeter cubed of sulfuric acid, concentration 0.05 mole per decimeter in a conical flask. Add 0.2 gram of zinc powder to the conical flask. Put the stopper in the conical flask. Measure the volume of gas collected every 30 seconds for 5 minutes. Repeat steps 1 to 4 with sulfuric acid of a concentration of 0.1 mole per decimeter. Figure 8 shows the apparatus used. Lovely. Don't you just love huge stems to questions? So the student made an error in setting up the apparatus in figure 8. What error did the student make? So they have put the acid in. They've put the gas syringe in so the gas can be collected. Look what they've done. Where have they put the gas syringe? What's going to come bubbling up here? Hot acid. We want to collect the gas, but instead they're collecting the acid or the reactants. Really, this tube should not be in the acid. So, delivery tube is in the reactants. It should be in the air above. So the delivery tube should be in the air above the reactants. So i.e. it should stop about there so that it's actually collecting the gas and not sucking up acid, which is what will happen. Okay. The student corrected the error. Woohoo! Figure 9 shows the student's results. Now they've made it better. So volume of gas, we've got a line which shows the experiment done when they used 0.1 mole. And you can see here, this is the higher line with the dashed line. This is when they used 0.1 mole per decimeter. And then they halved the concentration to 0.05 mole per decimeter of sulfuric acid. And this is the solid black line here, which is lower. Explain why the lines of best fit on figure 9 become horizontal. So why is it that the lines level out? Of course, notice the higher concentration levels out first and the lower concentration levels out later, but both level out. And why is that? So the reaction is over. All of the acid or reactants are used up. It might not be the acid, it could be the zinc or whatever they were adding is used up. So no more gas is released. No more hydrogen gas is produced. And that's going to get you the 2 marks. There's no more gas coming out. That's what it tells us. And that's because the reactants are used up. So no more gas because reactants are used up. Lovely. 9.3. How does figure 9 show the zinc powder reacts more slowly with 0.5 mole per decimeter sulfuric acid than 0.1? So if we look back at that graph, guys, how can we tell that the solid black line is going more slowly? Look at the time. So in the same amount of time, less gas is released, but we can visually just say that the line is shallower or not as steep. So the higher concentration is steeper. So we want to say the line is not as steep, and that would be visually how figure 9 shows. The line is not as steep. They love the word steep in these. Okay, we got a calculation. Determine the rate of reaction for 0.05 mole per decimeter sulfuric acid at 80 seconds. Show your working, give your answer to 2 significant figures. Essentially, you'll get most of the marks even if you get all some of these points wrong. So let me just show you. I'm going to zoom in a bit here and try to do this a little bit more accurately. So we want to go to 80 seconds and we want to zing up. My 80 seconds is there. So we're going to make a dot here. I'm now going to remove my line. I'm going to switch colors. I'm going to use brown. And I need to do a straight line. Now, this is probably where it's not going to be as accurate for me because, no, that's just pants. So I need to go through that so it's roughly the same either side. The problem with doing this online is I can't rotate this line, can I? I can rotate. No, I can't do that. All right, I've got to get this right first off. Does that look right? You know what? I'm going to go with that. I'm going to go with that. Okay, so here I've gone up to 32, 33, and I'm just going to stick to there. And it doesn't matter whether I do this above or below. Like I could do a triangle like that. I could do the top triangle or the bottom triangle. I'm just using this bottom one here. And essentially what I've got to do here is this is the y-axis, this is the x, and we've got to do y over x, remember. Let's see if I get a similar number. Right. So that looks like 33. And I'm going up to 64. So a totally different number here. 64 and minus 33, which doesn't matter because I'm using a different size, but let's just see. So that is 31. That looks like, so that's 64 to 33. Yeah, so we've got 31. And then for the x-axis going across, I've got 0 over here, and we're finishing on 150, which is lovely jubbly. So I am going to get the same answer as I got before. So this was just me to confirm it for you. I'm going to get a very similar answer that, oh, no, it's not really the same as I went before. Okay, I got 0.206. I think this is the better answer. So because they wouldn't have asked for two significant figures. So I'm going to round that to 0.21. And that's given me two significant figures. So 0.21. And that is going to get me 5 marks. So 1 mark for the dot, 1 mark for drawing the tangent. Should be roughly even this area on both sides of the curve to the eye. Then drawing that, then doing y over x, and then rounding to two significant figures. That will get you your 5 marks. Okay, 9.5. The activation energy for the reaction between zinc and sulfuric acid is lowered if a solution containing metal ions is added. What is the most likely formula of the metal ions added? So if you're lowering, what do we know about what things lower the activation energy? What lowers activation energy? Hopefully you can spot which is a catalyst. What type of metals in the periodic table make good catalysts? So hopefully you'll understand it's going to be a transition metal. They're found in the middle of the periodic table, and those make good catalysts. So it's most likely to be that. Okay. Last question. Finally, question 10. The question is about alkenes and alcohols. Ethene is an alkene produced from large hydrocarbon molecules. Large hydrocarbon molecules are obtained from crude oil by fractional distillation. Name the process used to produce ethene from large hydrocarbon molecules. And this is cracking. So cracking is when you take large hydrocarbon molecules and you split them into smaller ones. And we're now asked for describe the conditions used to produce ethene from large hydrocarbon molecules. So you normally need a very high temperature. So we're going to need high temperature. I don't know, let's go 650 degrees, vaporize, pass over an alumina catalyst. Now, there's loads of different catalysts you can say. So I want to vaporize it. So I'm going for 650 degrees. And then once the hydrocarbon is vaporized, you pass it over an alumina catalyst. Now, what is alumina? Alumina is aluminium oxide, so you can just say aluminium oxide. You can say silicon oxide. You can say silica, which is another name for silicon oxide. Yeah, great. And this will get you all the marks. Oh my good gosh! Another 6 marker and another one. 10.3, ethanol can be produced from ethene and steam. The equation for the reaction is ethene plus water goes reversible reaction to C2H5OH. The full reaction is exothermic. Explain how the conditions for this reaction should be chosen to produce ethanol as economically as possible. So we need to think about economics. We need to think about yield, how we can get the highest yield. Now we need to think of the information they've told us. It's exothermic, and I always like to think as we did one of these exothermic. I always think of those as hot reactions. And you shouldn't really ever write hot in the exam in terms of in an answer, but I'm just putting it as a note here. Endothermic, I like to write in blue. Obviously, you can't do that in the exam, but endothermic are cold reactions. And then we need to use a bit of Le Chatelier's principle here. So if I use a high temperature, which direction is this reaction going to shift? Remember Le Chatelier, or yeah, Le Chatelier said, if you increase the temperature, the reaction will do the opposite, and so it will try to cool down. So if I make the reaction warmer by increasing the temp, the reaction is going to go this way, and I'm not going to get a lot of ethanol. It's going to decrease my yield of ethanol. So using a high temperature will shift the equilibrium to the left, to the endothermic side of the reaction, and will decrease the yield. So we should not use a very high temperature. This will also save on costs, as temperature requires heat energy, which is expensive. Okay, a little bit of waffle about cost. So we shouldn't use a high temp. However, there's a big however coming here. What happens if we use a really low temperature? However, a low temperature will mean a slow rate or a low rate of reaction. So we need to use a compromise temperature here. So we're going to use a compromise. So not too low, not too high. Okay. Using a catalyst will cost money, but will enable the use of the lower temperature to get a higher yield. Now, what about pressure? We need to consider pressure as well. So when you look here, we've got two gas molecules on this side and one gas molecule on this side. Now, this is good news for us because it means if we use a high pressure, it's going to force the equilibrium and shift it to the right, meaning a higher yield. So use of a higher pressure will shift the equilibrium to the right, as this is the side with the least gas molecules. Remember, Le Chatelier says it's going to do the opposite, the reaction of what you do. So if you increase the pressure, it's going to say, geez, I want to reduce pressure. So it's going to go to the side with less gas molecules. So actually increasing the pressure here is a good thing because the reaction will try to reverse our change by shifting to the side where there's less gas molecules. So using a high pressure will shift the equilibrium to the right, as this is the side with the least gas molecules. Okay, this will increase the yield. So this will increase the yield. Again, however, we need to make a little compromise. So this will also increase yield. However, high pressure is dangerous, as it could lead to explosions. So we need safety equipment is expensive, so we need to use a compromise pressure. Compromise pressure means high but not too high. So maybe 200 atmospheres or something, but you don't want to use like 1,000 atmospheres because that could lead to explosions, would mean you need really thick steel walls around your reaction vessel to prevent explosion. And that's going to get you all 6 marks. We've taken into consideration catalyst, we've taken into consideration temperature, reaction rate, and the shift in equilibrium with yield. We take into consideration pressure and the safety side of pressure and the expense of using a high pressure, but also the fact that a high pressure in this reaction leads to a high yield. So boom, bam, bish, bosh, bash, 6 marks. Okay, 10.4, ethanol can also be produced from sugar solution by yeast. What's the name of this process? It's fermentation. And that's another way of making ethanol um, by using yeast and sugar. This is how they make drinking alcohol. 10.5, butanol can be produced from sugar solution by adding bacteria. Sugar solution is broken down in similar ways by bacteria and by yeast. Suggest the reaction conditions needed to produce butanol from sugar solution by adding bacteria. So, we want 30 degrees temperature as too high above 40 degrees will denature enzymes. I'm just writing a bit more for explanation, but I would suggest 30 degrees temperature. If you go above 40 degrees, will denature the enzymes. Below 30 degrees would be too cold. We want to do butanol from the by adding, yeah, so the sugar is going to provide them enough so that they can survive and they can produce. What else do we need? What else? What else? What else? We're nearly done. Um, and maybe anaerobic conditions. Yeah. If we give them aerobic conditions, they might not make the alcohol because the fermentation to produce alcohol um, normally requires a lack of oxygen. It's an anaerobic form of respiration. Okay, ethanol and butanol can be used as fuel for cars. 10.6, a car needs an average 1.95 kilojoule energy to travel 1 meter. Ethanol has the energy content of 1,300 kilojoules per mole. Calculate the number of moles of ethanol needed by the car to travel 200 km. So this is just like a maths equation. Some of you will be a lot better than me at maths. So the fact that we got 200 km and 1 meter, I want to turn that into meters. So we're going to times 1,000, and that means we're going to have 200,000 meters. So now we're talking. So first of all, we need to know that the car is going to go 200,000 meters. So the car is going to burn that much fuel. So we're going to go, is going to need that much. So I'm going to go 200,000 times 1.95 kg. We know that 1 meter uses 1.95 kg. So how much will 200,000 use? Well, we need to do 200,000 times 1.95, and that equals 390,000 kilojoules. So we've got at least 2 marks here. We've got a mark for the conversion here. We've got a mark for coming up with that there. And then the final mark, calculate the number of moles of ethanol. We know that there's 1,300 kg per mole. So we need to find out how many moles this is. Well, if there's 1,300 kg per mole, we're going to divide that by 1,300, and that is going to give us 300 moles of ethanol. And that is our final mark. So for doing that there. Beautiful. And the final part to the question, 10.7, when butanol is burned in a car engine, complete combustion takes place. Write a balanced equation for the complete combustion of butanol. You don't need to include state symbols. Wunderbar. So butanol is C4. Blah, blah, blah. H9OH. Hold on, is butanol? Hold on. Gonna double check, folks. I should know my alcohol general formula off by heart and be able to work that out, but I'd be lying here and say I can't remember it. So we've got 4 carbons. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens, like I thought, round the sides. And then we have OH. OH. Boom. We're cooking on gas. Now it probably gave me the formula above, and I'm such an idiot that I didn't look. And what do all combustion reactions produce? If they're complete combustion, and it says complete, they make CO2 plus H2O. Now, these are the easiest equations to balance in the world. And there is a reason, because you just look at the number of carbons, you go, ooh, 4. You look at the number of hydrogens and go, 9 and 1 is 10. So I'm going to need a 5 there. 5 times 2 is 10 also. Boom. Now we do the oxygens last. 4 times O2 is 8 oxygens. 5 times O is 5 oxygens. That combines to tell me that I have 13 oxygen atoms. You might go, oh my God, an odd number. What can I times? You just go 6.5 or 6.5 times O2. This is the only combustion reactions where they'll allow you to use fractions. Some teachers like you to say multiples, so then they times everything by 2, but then you've got to times that by 2, that by 2, that by 2, that by 2. So you'd have 2 lots of that, 13 lots of that, 8 lots of that, and 10 lots of that. I don't like doing that. I like to use the fractions. So there we go. Bish bash. All done. Don't forget to share, like, subscribe, hit the notifications. Let's get to the mocks.
You're still here? It's over.
Let's move on. Moving on.